Welcome to the ninth lecture from chapter number 9. We are studying VLSI design, and today we will study dynamic CMOS logic. In our last lecture we studied that a dynamic CMOS is a kind of circuit for which the output is valid only when the clock is 1. The output is not valid as long as the input is valid, as it is in the case of static CMOS. For a dynamic CMOS, output is only valid when we have a valid clock. If we do not have a valid clock and if the input is valid, the output will not be valid. Right. So the block diagram of a dynamic CMOS logic is given here. We don't have a PMOS array. And we don't need to have that. We only have an NMOS array. So it's a circuit that gives us better speed compared to CMOS, and we need lesser number of transistors to implement this logic, because instead of having a full-fledged PMOS array, we only need two transistors, one PMOS and one NMOS transistor. They are connected, their gates are connected together, and they are connected to the clock phi. In contrary to the C-squared MOS that we studied in last lecture, we don't have two clocks here. We only have one clock. In that case, in C-squared MOS, we have two clocks, the clock and its complement. Here we only have we only have one clock, phi. That is also a square wave, 0 and 1. So it keeps on moving between 0 and 1. So when it is 1, the output is valid. When it is 0, the output isn't valid. So the pre-charge for the pre-charge mod, phi is 0. When phi is 0, we call it the pre-charge mod. In pre-charge mod, when phi is 0, this PMOS is on. MP has to be on. And what's about MN? It is off, because to turn this MN on, we need VDD here. And what's about Vout? Vout is, this output is actually Vout. Vout is VDD, because this NMOS array is not on, because this transistor is not on. Even if we have inputs that turn on this NMOS array, the 0 won't reach there, because this transistor is getting the whole output, this whole array. If this transistor is on and this NMOS array is on, only then this 0 can appear out at the output. So when we have phi is equal to 0, this NMOS array is disabled and the output is 5 volt. And when we have phi equals 1, we call it evaluation mod. In this mod, this MP transistor is off, whereas MN transistor is on. This MN, this is MP transistor. MN transistor is on, and Vout is the function of input. Whatever is the function being performed in this NMOS array, that function would be available at the output. Right. To graphically show what these mods are, we can represent it like this. We have this pre-charge here and evaluation here. As time goes on, this is phi as a function of time, and then we have pre-charge, and then we have evaluate. It keeps on going. Right. Now we are ready to erase everything that we have on the board, and we'll implement a simple circuit using dynamic CMOS. The expression that we are going to implement is this: A dot B dot C, the whole complemented. This is a NAND 3 gate. A NAND 3 gate, the PMOS array, we have to implement the PMOS array as we have just studied, A, B, C, and then we have this gating NMOS, and on the top of this NMOS array we have the getting PMOS transistor. So these two transistors are the getting transistors MP and MN, and here we have this output. This is connected to VDD and this is connected to phi, right? So this is how we can easily implement any circuit, any boolean expression. We have to just implement the NMOS array. We can put this NMOS array in a box showing that this is the NMOS array and these two are getting transistors. So we can implement any given circuit, any given boolean expression, the schematic of any boolean expression by implementing NMOS array and these connecting these two getting transistors. So, and then we have to discuss some disadvantages. Up till now, this seems to be an advantageous circuit, the dynamic CMOS, because we use less number of transistors, we need less number of transistors, and it is fast. It is faster compared to CMOS. But we have some disadvantages. A disadvantage is the major disadvantage is charge sharing problem. Suppose we are using this circuit and we are working in pre-charge mode where phi is equal to a 0. This means that the output is supposed to be at VDD when we are working in, suppose we are in pre-charge mode. In pre-charge mode, the output would be VDD because phi is on, this transistor MP transistor is on, MP is off. So Vout is VDD, and suppose we have the inputs A is equal to a 0, B is equal to a 0, and C is equal to 0. The output is VDD. But if we have any of the two inputs is equal to a 1, if we have this condition, the output C would be the charge accumulated at the output capacitance C out times VDD. The charge accumulated on this capacitance would be C out times VDD. But if we have any of the three transistors on, suppose we are discussing this situation where this A is equal to a 1, this B is equal to a 1, and C is a 0. This means this transistor has an output capacitance, so let's call it C1, and the voltage across it is V1. And this transistor will also be having a capacitance C2, and let's call the voltage across it is V2. So we can write in this scenario Q is C out, but this VDD would be shared between this. So this VDD would be lesser, this V out would be lesser than VDD in this case. V out would be lesser than VDD because there is some current flowing through it, dropping its voltage from VDD down to a lower value. So this V out, suppose it settles at a value equal to, let's call it Vf, and we assume that the resistance of these transistors, assuming Rn is very small and it approaches 0. If Rn is 0, this capacitance, and this capacitance, they come in parallel. If we have a 0 resistance here, 0 resistance here, this means these are the same. All these three terminals are the same node. These three terminals are the same node if we have a 0 resistance here and a 0 resistance here. So assuming that Rn approaches 0, Q is, and if they are the same terminal, this Vf appears here, this Vf appears here, and the same Vf appears here. Assuming there is no resistance here, they are the same node. Then we can write it as C out plus C1 plus C2 times Vf, or we can multiply Vf with each term first and then take Vf common. Vf plus C2 Vf, and then we can take Vf common, take out Vf common, so this charge becomes Vf times the sum of these three capacitances. So this gives us another equation, let's call it equation number 2. Now we have one equation when there was no loading effect, when all these transistors were off, and it took us to this equation where Q is C out times VDD, and when we have turned two transistors on, we reach here. But the left hand side of both equations 1 and 2 is the same, so we can compare them together. So we can compare these equations and we reach C out VDD is C out plus C1 plus C2 times Vf. So Vf comes out to be C out over C out plus C1 plus C2 times VDD. So this fraction will always be having a value lesser than 1 because the denominator is always greater than the numerator. So this gives us a number that is smaller than 1. So Vf is always lesser than VDD, which is quite logical. It has to be, because there is some leakage current flowing through the capacitances of other paths. So, which is not good because the output should be equal to VDD when we are in pre-charge. The output is supposed to be VDD. So how to make it closer to VDD, as close as possible? How to take Vf close to VDD. It's a question how to make it closer to VDD, because we want it to be VDD, we are in pre-charge, and it has to be equal to logic 1. So how to do that? Make this fraction as close to 1 as possible. So how would you do that? For that, C out should be much greater than C1 plus C2, but having large C out has other problems. You know what is the problem of having a larger C out? You know that, large delays. So having larger value of V out will take us to larger delay. So it's a compromise. Everything is a compromise. We'll continue studying high-speed circuits in our next lectures. Thank you.